Okay, looking at the single problem that I gave you for Chapter 18, here's the Chapter 18 worksheet. Suppose that your body has a net charge of plus 2.5 microcoulombs. Remember, mu, the Greek letter mu, equals micro. That's how we pronounce it when we put it as a prefix. And it's equal to 10 to the minus 6. So your body has a net charge of 2.5 microcoulombs, while your friend has a net charge of 2.0 microcoulombs. You're both positive charges, so I'm going to draw a picture right off the bat. You are here, and your friend is here. And we have Q1 is equal to 2.5 microcoulombs, and Q2 is equal to 2.0 microcoulombs. And reading the problem further, it says that they are separated by a distance of 0.75 meters. So there I've got a picture to show everything. And the first question is, what is the direction of the force? So we just think about our rules, and our rules for the electric force is that opposites repel, opposites attract, likes repel. So these are likes, so the likes are going to repel. So the force of person 2 on 1 is going to be going that direction. The force of person 1 on 2 is going that direction. So they're repelling. So what's the direction of the force? Because it doesn't give us any x, y information, I'm just going to put here, it's repelling, pushing away. What is the magnitude of the force? Now, for the magnitude of the force, we use Coulomb's law. Coulomb's law tells us that the magnitude of the force is equal to K Q1 Q2 over the separation squared. So in this case, R is D, and I just put in my values. That's 8.987, 9877, something like that. I'll put 988, and that way I know I'm right. Times 10 to the 9th Newton meters squared per Coulomb squared. That's my K. Charge 1 is, and I'll just color code it to match, 2.5 times 10 to the minus 6 coulombs. Charge 2 is 2.0 times 10 to the minus 6 coulombs. Let's keep the colors smooth here. And then we need to divide by the separation squared. So divide by 0.75 meters quantity squared. Well, you put that in your calculator, and out comes 8.0 times 10 to the minus 2 newtons. So there's the magnitude of the force. And I'll put C for Coulomb. Now notice there's only 2 digits here, 2 digits there, 2 digits there. So since these are all multiplied and divided, I have 2 significant digits in my answer, so that's why I just have 8.0 times 10 to the minus 2. If I'd wanted to keep one more, it would have been 7.99 times 10 to the minus 2 newtons. But we only had 2 significant digits, so I just put in 2. Now ask, what's the electric field at your location due to your friend's charge? Well, there's really 2 ways to do this, but the way that I am going to do it here is, so this is part C. I'm going to use the electric field magnitude equation, KQ over R squared. This is the magnitude, so I don't have a vector sign, of the electric field at your location due to your friend's charge. So that means the Q is going to be Q2, your friend. So it's going to be and this time I only am going to have the red charge, the friend's charge. And then I again have to divide by my radius, 0.75 meters is the separation, squared. And when I do that calculation, it's going to give me 32,000 newtons per coulomb. Now you might say, how does he get newtons per coulomb? Well, notice meters squared divided by meters squared, those cancel. Coulombs divided by coulomb squared leaves a 1 over coulomb, and the newton was left over, so newtons per coulomb. In the same fashion, when I found the force, I had coulombs times coulombs on top, coulomb squared on bottom, so those units canceled. Meter squared on top, meter squared on bottom, those cancel, leaving just newtons. All right, so we've got A, B, and C done. Part D, what is the magnitude of the force using the electric field? So the reason I did part C the way I did is because part D, what is the magnitude of the force? I'm going to do the definition that force is equal to QE. So in this case, that electric field is electric field due to charge 2. This is going to be charge 1 caused by electric field 2. So that's going to be my charge 1 of 2.5 microcoulombs. Let me put times 10 to the minus 6 there. And then electric field due to the second charge, 32,000 newtons per coulomb. And that will equal 32. It'll equal 8.0 again. 8.0 times 10 to the minus 2 newtons. So we get the same answer. Obviously, 2.5 times 10 to the minus 6. 25 is a quarter. So 32 divided by 4 is 8. So you can see where we get the 8 from there. Don't have to pull out a calculator to see that. And then finally, draw the combined electric field in the region within 5 meters of the point midway between you and your friend. So now I'm going to have to be a little more careful. Here's you plus 2.5 microcoulombs. And here's your friend, 2.0 microcoulombs. And so we want the region that's within 5 meters. So basically what we have on the screen now. So we know that the electric field, if these were in isolation, the electric fields would just go out from each other or from each charge. So I'd have electric field like that from that one, and except for there need to be a few more lines from you because you have a bigger charge. So instead of making it 8, I'll make it, and of course I'm not actually getting the ratios right here because, well, not that good. So there I have, I believe, 2 more lines. So this one had 3 and this one has 4, going both directions. Not exactly right. Now when we combine these, what it's going to do is it's going to make a picture that is a little biased by the larger charge. So I am going to redraw up here the 2 charges, and then they're going to still come out like that. And this here is going to come out, and it's going to be met by one coming out from this that's not as strong. And then I have to try to figure out the rest. So since this is the stronger field, it's going to be a little more dominant. So it's not quite symmetric. And of course I started doing it for charges that were the same, or opposite side, I mean. So there's my rendering of what it's going to kind of look like. And you have a region here where the lines just don't touch. So there's my electric field lines going out of positive for the combination of the two charges, with the black charge being slightly bigger in magnitude than the green charge. All right, so that's the problems for the chapter 18 worksheet, the problem.